So moving on here to chapter 13, but a little joke beforehand about it. You know how dumb the average guy is? Well, by definition, half of them are dumber than that. Kind of a math joke about means and averages, but let's go ahead and move on to chapter 13. So chapter 13 is about experiments and observational studies. You can pause the video and read this if you want to. Okay. Very briefly, we're going to talk about how we set up experiments, the difference between experiments and observational studies, blocking, replication, what statistical significance means. We'll talk about randomization of one-factor, two-factor designs. Now, observational studies, very simple. Observational study, the researcher did not assign a treatment. This is just, they observe what's going on. Researcher goes out, counts the number of eggs in a nest to see how many eggs birds are laying. That's it. It's an observational study. They're not changing anything. They're not messing with anything. Now, observational studies can come in two varieties or two flavors. Retrospective, they're gathering information about the past, or prospective, they're watching to see what happens in the future. For example, if I follow some people along for 5 years, that's a prospective study. I'm following them to see how it works. But instead of just asking them what happened over the last 5 years, that's retrospective. I'm asking about the past. Additionally, we now have experiments. Experiments are where the researcher imposes a treatment on a randomly assigned individual in order to observe the change. Now, the person doesn't have to be randomly chosen from the population, but they do have to be randomly assigned to the different groups we're going to deal with. So again, randomization does not mean I need to get a random person from the population, because usually experiments use volunteers, but I do need to randomly assign them to the different treatment. We'll go over how we do that. Now, experimental units, very simple, the individuals we experimented on. Now, when it says individuals, don't think that means people. It could be anything. It could be radios. I want to see how long different batteries last for different temperatures. So I take my batteries, I have some in the freezer, some in the air, and then some that are actually heated up using an oven. The batteries are the individuals I'm experimenting on. However, when the units are human, we call them subjects. Don't call humans units. It's just not polite. Now, response variable, we need to identify it. We need to measure it in any experiment. In this case, it's going to be how long does the battery last at those different temperatures. So how long does the battery last? That's my response variable. Factor, that's the explanatory variable that we need to manipulate in any experiment. So in this case, I'm talking about batteries. The factor is the temperature that the battery is being kept at. Now, level, it's the specific values that the experimenter chooses for a factor. I said I keep one in the freezer, one at air temperature, one has been put in the oven. So my levels, I have 3 levels. I have the freezer, air temp, and oven temp. Those are my 3 levels. Now, last we have to know is how many treatments were involved. The way we do this is we look at the level times the level times the level. What I mean is, for each factor, there are a certain number of levels. In this case, I had a battery at 3 levels. The temperature, there were 3 levels. There were no other factors. So my treatments equals 3. There are 3 possible treatments. Now, I could also have said, I'm also going to do a factor of the amount of current I'm drawing from the battery at a particular time. I might have 3 levels for that. So I'd have 3 temperatures, 3 different levels, and that's 3 levels. And then I have 3 different current draws. That's 3 levels. So I have 3 times 3 to get 9 total treatments. I'd have to have one that was cold. I'd have to have 3 batteries that were kept cold and draw at all 3 different current levels. 1 battery and 3 batteries at air temperature with the 3 different current levels. And 3 batteries have been in the oven at the 3 different current draws in order to see. So I'd have to have 9 treatments. Now there are 3 or 4 principles of experimental design. Now, primarily there's 3, but there's sometimes a 4th. First one is a control. I need to make sure the sources of variation, other than the factors we're testing, have little to no impact on the response variable. In other words, I don't want to have anything else fluctuating or changing. As much as possible, I want to have only the factors that I'm changing possibly affecting the outcome. So I need to exercise some control over the experiment. Don't have other things changing. Just the factor I want to change. It reduces the variability in the responses. It makes it easier to detect the differences. I'm not worried about something else caused the difference. Second, I need randomization. I need to assign subjects to treatments randomly in order to use the method of statistics to draw conclusions. I want to create groups that are similar to each other in order to equalize the effects of unknown or uncontrollable sources of variation. So I need randomization and who gets what treatment. Next, I need replication. I need to repeat my experiments on many subjects or many units in order to reduce the variation in the results. What I'm saying is you can't do an experiment if there's only one person taking the medication. I need a lot of people taking this medication. I need a lot of radios being tested. I need a lot of batteries being tested. And sometimes we have a fourth one. That fourth one is called blocking. Now we use this to minimize variation. So a block is a group of units or subjects that are similar in ways that are expected to affect the response. And what I'm saying is, let's say I wanted to do something about how people lose weight. And I'm going to have a medication that's potentially going to help people lose weight. Well, I might need to block. I might need to block by gender because men and women have different physiologies. They may react to the medication differently. So I need to, before I assign anyone to anything, I set up blocks of all male and all female. Once I've done that, then I deal with each block individually and who gets treatment and who doesn't get treatment. So treatment is assigned randomly within the blocks. Blocking is a form of control, and you better use it if there's a variable that could affect the outcome. Now, some of the most common ways, often block on age, gender, race, but you can block on any characteristic which you think could act as a lurking variable if we don't account for it. Now, for example, maker of Frumpies. They make the breakfast of Rugrats. They want to improve their marketing. So they ask you, first, they want to know what fraction of kids aged 10 to 13 like their celery-flavored breakfast cereal. They ask, what kind of studies should I perform? Well, all we want to know is what percent of kids like their cereal. That's just a survey. I ask a randomly selected group of kids, do you like the cereal? We want as little bias as possible in the question. We don't ask them, we don't give them any information about the cereal. We don't even say it's celery flavored. They may not know it tastes like celery, so they may like it. But if you told them it tastes like celery, maybe they wouldn't like it. So you just say, do you like the cereal? Well, now they're thinking about putting on new flavor. They're going to make maple marshmallow Frumpies. And they want to know whether children will prefer the new flavor to the old flavor. So now we design a completely randomized experiment to investigate. Now, completely randomized means we're not going to exercise any control on who ends up inside of what group other than a random process. Well, we could do something like this. We take all of our volunteers, here, and we use a random process to assign them to group 1 or group 2. Group 1 receives the new flavor, group 2 gets the old flavor. After they've had a chance to try it, we ask them what they thought, and we compare what percent liked it. Now, this is a partial credit. This is a partially complete answer, but it is not all the way complete. All the way complete, I start with the same diagram. Still want to include the diagram. But now I explain how will I randomly assign. Well, each volunteer gets a number from 1 to 30. I then will use 2 digits from a random number table, ignoring repeats, 0, 0, or any number greater than 30. The first 15 numbers I select, they get the new flavor. So I've randomly assigned them to the new flavor or the old flavor, because everyone else goes the old flavor. Then I compare the results. This is a full credit answer. This covers everything you have to cover. Okay? If you skip out how you do the random assignment, you're partially there, but you have to tell me how you plan on doing it. And it needs to be a legitimate process for a random assignment. Now, next thing is now they think actually kids who watch the Saturday morning show with Frump, the flying teenage warrior rabbit who eats Frumpies in every episode, they think those children may respond differently to new flavor. So how do we account for that? Well, that's a variable that we think is going to affect our response. So now we have to do some blocking. We take our volunteers, we block them. Those who watch Frump and those who don't watch Frump. In the ones that watch Frump, we use a random process to put them in group 1 or group 2. Group 1 gets new flavor, group 2 gets the old, and then we compare the ratings. Now I take my kids who don't watch Frump, and again, a random process to group 1 or group 2. Now they get new flavor, old flavor, and again, compare the ratings. This is how I use blocking. I think watching the show affects the response, so I block based on that variable. But again, the random assignment now was within each group. Each block gets a random assignment. And again, describe it. How would you do that random assignment? So we're looking at the differences between the groups. We do think there's some difference just because of random variation. The big question is how big that difference has to be before we say it's the effect of the treatment. What we're talking about is a thing called statistical significance. You need to know this. Statistical significance is when a result was too unusual to just have been caused by chance. Okay? And we're going to worry about what that value is, but at this point you need to understand statistical significance is when an observed result was too unusual to have just happened by chance. So control group. We're always going to have a control group. This is different than exercising control. These are the people who get a dummy treatment. They are getting a treatment. This is a level. It's just that it's set at 0. They're not going to get anything, but that is still considered a treatment. You have to count this as a type of treatment. It helps us account for lurking variables. So there's something underlying everything that could be affecting it. This is how we find that. We don't find the variable necessarily, but we'll still have that effect happen. But since we didn't give them any medication, we didn't actually give them a treatment, this is our baseline. Our baseline will include that lurking variable. Now, placebo, that is a dummy treatment that has no physical effect. This is what you give your control group. Okay, placebo effect. Some percent of people are just going to get better no matter what you do. Some batteries are going to last longer than others just because they are. That's our placebo effect. Okay. If you remember Harry Potter, he thought he gave him the truth serum, but they actually didn't. But he told the truth. That was a placebo effect. He would have told the truth regardless of actually getting the truth serum. Okay. Now, blinding. This is pretty important in experiments. You may have heard about calling blinding experiments. This is where some of the people associated with the experiment don't actually know who's in what treatment group. Now, this is where we want to do some blind. We don't want people to know they're trying Pepsi or Coke until after we find out which one they prefer. It reduces confounding variables because we don't have the opportunity to introduce that confusion. Okay? Now, there's two classes of individuals who can affect the outcome of the experiment. First of all, those who actually influence the results directly, the subjects who are taking it, the treatment administrators, or technicians. Secondly, those who evaluate the results. If you're talking about a judge, the physician who's going to evaluate the results, all of these people could affect the outcome of an experiment. So single blinding is when all the individuals in one of these two classes is blinded. They don't know who got what. Often single blinding is when the subjects don't know who got what. The administrator doesn't know who got it, or the technician doesn't know who got it. But the physicians in the background may still know which person got what before they've evaluated the response variables. They know who got the actual medication. Now, double blind, no one knows. The doctors just have to evaluate the response variable and see if they detect any differences between groups. But they don't know which group got what. They want to see if they can find a difference. And usually, if they can, that means there was some effect. So double blinding is important, and if you can do it, you want to do it. The thing is, if a doctor is giving medication, and they know who's getting the real medicine, and they know who's just getting a sugar pill, they might treat that patient who's getting the sugar pill a little differently. They might pay a little bit more attention to vital signs. They could treat them differently and affect the outcome of the experiment. So double blinding is really kind of our gold standard of the best, if we can do it. It's not always possible. Okay? As we said, it's usually double blinded, but good experiments need to have randomization, random assignment to the treatment or control group. Double blinded, I was just saying, beating that horse down. Comparative, I'm comparing the control group to those who got the treatments, and if there's multiple treatments, the treatments to each other. And placebo controlled. So it's not just I'm comparing to people who we do nothing with, but they think they're getting the treatment when actually they didn't get anything that will cause an effect. Now, types of experiments. One of those is, we've talked about completely randomized design. We also have matched pairs. This is a kind of blocking for comparing two treatments. I want my pairs to look alike. The most common one for this, if you can do it, are identical twins. Identical twins who grew up together, well, genetically they're same. They grew up in the same environment. Hopefully they're still about the same. One of them gets the treatment, one gets placebo. Later on, we see if the treatment had any effect. They don't have to be identical twins. I could say team up two people of the same race, approximately the same age, same gender. One gets treatment, one gets the placebo treatment, and we see if there's a difference. Now, the other one we can do is a before and after situation. I have the same person take the before test, they then receive the treatment, and then they take the after test. And that after test should look very similar to the before test. Purpose of this, did treatment improve test performance? I might do one of these in class where what I'll do is I'll give you a pre-test before we actually learn a new subject. After we learn it, you'll get the post-test. This was a matched pair. I'm going to compare your results on each test, but only to yourself. I want to see, did you improve between the two? This is a matched pair design. Now, we want to be aware of lurking variables and confounding variables. Lurking variables are common in observational studies. They're very common in observational studies, where we think there's an association between the two variables, but really they're just each responding to a third unseen, untracked variable. We talked about this. Now, some different examples. What about ice cream sales and drownings? Well, when ice cream sales go up, drownings go up. There's a positive association. But which one's explanatory and which one's response? I mean, is it explaining the change in drownings? Are drownings explaining the change in ice cream sales? So it's a little difficult. Should we conclude that when people are sad to hear about drownings, so they attempt to cheer up by eating ice cream? No. More than likely, is it dangerous? You had ice cream and then you go swimming, so you're more likely to drown? Oh, really what's going on is probably the summer heat. If it gets hotter out, people eat more ice cream. And they're going swimming more often, there's probably more drownings. The summer heat was our lurking variable. How about the positive association between the number of firefighters at a fire and the amount of damage? Maybe you shouldn't call the fire department. Too many firefighters show up, there's going to be a lot of damage. Well, maybe not. Maybe it's the size of the fire. It causes more damage, and that's going to get more firefighters to show up. If you've ever heard about 2-alarm fire, 3-alarm, or 5-alarm fire, had to do with how many fire stations got called. And a 5-alarm fire, they were calling out a lot of firefighters to fight that fire. Okay. Now, be aware, these are kind of large, easy to see examples. Now, I don't want you to think that lurking variables are always obvious or going to be silly. Okay, usually they're more subtle. The main point of having to do with lurking variables is we don't want to infer causation just from association. I know I kind of beat that one down. We cannot assume causation just because of association. We need to have experiments to talk about causation. Now, confounding variables are a little different. This is when the response we see in an experiment is partially attributable to some uncontrolled variable. This isn't the same as lurking, although it's similar. Lurking is something that's happening that's affecting both. Confounding is at least driving one of them, but may have nothing at all to do with the treatment. So there's a confounding variable. There's a variable introducing confusion. So it's causing a change in our response variable, has nothing at all to do with the treatment potentially. Okay. The issue is, how do we tease apart what was caused the observed effect? Now, usually it can occur because of poor design. Now, good news is, blinding kind of takes care of or at least reduces confounding. Let's say I'm doing an experiment. I want to see how my geometry class is doing. And I'm going to compare it to Miss Will's geometry class. But then we find out that my room is kept at 60 degrees and her room is kept at 80 degrees. That variable, if I want to know who was a more effective teacher, that variable 60 to 80 degrees, that's going to be a confounding variable. It's going to cause change. Potentially, it could cause change in the results. If you're in a room that's 80 degrees and you're kind of tired, you're trying to learn geometry, you might just drift off to sleep. Okay? So we won't know. Are the scores because of the teaching, or did the temperature cause a problem? So one of the things we want to do, we want to make the two groups as similar as possible. We want to eliminate that problem. Now, confounding is also be structural. Anytime a study takes place over some period of time, there are risks that things can happen during that time that will change a treatment or could cause a change responsible for the observed effect. So let's say Netflix. Netflix wants to run a subscription drive, and they're going to do a marketing thing in order to try and get more people to sign up. But then after they start it up and they have their different groups, some are being advertised to, some aren't, we get this large group of bad weather rolls in. A bunch of storms shows up. We get a lot of rain over a prolonged period of time. Well, special promotion didn't appear to increase subscriptions. It looked like it might have, but they don't know. What if the weather had just gotten bad? So everyone signed up, they stayed indoors, they rented a bunch of movies. The special promotion might not have done anything. Our effect was confounded by the weather. So confounding does not have to be something we introduced. It can be an external influence We want to pay attention and see if variables have changed while we're doing our treatments. Now, ethics. This is where it's a little interesting. I like the ethics of it. Ethics of experimentation can be difficult. Okay, let's take a look at a conclusion from Newsweek magazine. Of all the pre-college courses you can take, the highest level of mathematics one studied in high school was the strongest continuing influence on a bachelor's degree completion. Finishing a course beyond the level of Algebra 2, for example, trigonometry, pre-calculus, AP statistics, more than doubled the odds that a student who entered post-secondary education, college, would complete a bachelor's degree. Now that's what they came up with. That's their conclusion. But that looks like it might be an observational study. How could we do an experiment that would let us draw that conclusion? Well, I take a group of students, randomly who've completed all the way through Algebra 2, and then randomly assign the students. Some will get a course beyond Algebra 2, and the rest wouldn't. And then a few years later, compare the results. Why would that be difficult? Why would that probably even be unethical? So think about that. Well, I would literally be denying something to students. I'd be denying them education just to see if if getting the education increased the odds of them completing their education. It's probably unethical to deny someone education who wants it, because I would have had to randomly assign them to get the education, not let them choose. And if I was just letting them choose, do I know it's the math that was causing them to graduate, or is it the fact that they wanted to take more of an education that increased the odds of them graduating? So maybe I could never do this kind of study. Maybe I can never actually say what caused it. Okay. No, maybe there's some gray areas out there. How about animal studies? Is it okay to use animals for experiments? Does it matter if we're trying to develop a treatment that could save someone's life? Or what if I just want to test some mascara and make sure it's not going to damage someone's eyes? Well, does it matter? If I'm trying to save someone's life, is it okay to experiment with animals? What if the animal is going to survive the experiment? What if the animal is not going to survive the experiment? These are all ethical concerns that have to be thought about. When can someone actually consent to try an unapproved? What is informed consent? If I told you you only had a few months to live, would you volunteer for the experiment? Would you want to be part of the treatment group, or would you want to get the placebo? Is it ethical to let someone who's probably going to pass away in the next few months, let them volunteer to not receive anything at all, or even volunteer for a drug that could potentially speed up the progression of the disease? No, this is an ethical consideration we have to take into account. Right now there's an experiment being done called vaginal seeding. Children who are born by C-section get swabbed with material from the mother, or they get swabbed with a sterile solution to see if it has any effect on their health. Because previously, observational studies have shown children who are born by C-section had higher incidence of certain kinds of diseases or disorders, including like asthma and allergies. So they're thinking maybe being born by C-section is not a good idea, that being exposed to those bacteria when they're being born is actually beneficial. Some other people have suggested maybe it's the antibiotics the mother got during the C-section. But would it be ethical to not give the mothers those antibiotics if you're going to give them a C-section and actually expose them to potentially infection? So is this a ethical experiment? It can be tough to decide. What if it's okay to find out, can we determine if mastectomies are effective for treating breast cancer by randomly deciding who gets a mastectomy and who gets something less disfiguring? Talking about random assignment. Some people might say if you're going to randomly assign people to that, that would be wrong. They should only assign the people with the least dangerous cancer. But if it's the least dangerous cancer, it was the least dangerous cancer. That's a tough thing. How about this? Is it acceptable to drill placebo holes in a patient's skull so they and their doctor don't know if they get the experimental implantation of nerve cells as a treatment for Parkinson's disease? By the way, yes, that experiment was done. One doctor would come in, drill the holes in the skull. The next doctor would come in and either implant nerve cells or not implant nerve cells, do something else instead. So no one knew whether or not they got the actual, new idea of a treatment. This was a proved experiment. Okay. So last thing I want to talk about is a little thing that actually happened to the authors of our textbook. And it's kind of weird. I know. It's like you don't have enough things to read already. English is giving you enough to read already. But if you ask your parents, probably your grandparents actually, about polio, I'm going to tell you, this disease, hit a lot of kids and it killed a lot and it crippled a lot of others. So parents were afraid of polio, and obviously they had a good reason to. Parents were desperate to find out what was causing it and protect their kids from getting polio. Polio, the epidemic seemed to peak in the summer, so some people blamed them on swimming. So children were forbidden to go swimming. Other people thought maybe it was because of peach fuzz, that something on peaches was causing polio outbreaks, so kids were forbidden from eating peaches. Now, while all this was going on, they tried to get parental approval to try an experimental vaccine in hopes of preventing the disease. This vaccine, you actually gave them a small dose of polio to the kid. You actually had to expose them to the live virus. So if you're a parent, would you give permission for that? If your kid gets polio, there's a chance to be paralyzed for the rest of their life, or potentially have to live inside of an iron lung that does the breathing for them for the rest of their life if they get polio. But maybe this vaccine will protect them. They might get this vaccine and they'll be safe from polio. Maybe they'll get the vaccine and actually come down with polio. Now, in 1955, one of the authors was actually in the experiment. School districts sought permission from parents to use second graders as subjects. Parents who agreed were taken to the local vaccination site in the spring. So there was a long line of kids inching forward to get a shot. And the author said, we stood there watching and listening as each child reached the front of the line and cried when the vaccine was administered, because there's still a shot. Then every kid waited for their turn to cry. These are second graders. About a month later, they made a trip again for the second dose. Another line to stand in, another chance to cry over it. Now, after the summer polio season, the figures were checked. It was clear the polio had dramatically reduced among those who got the vaccine compared to those who got the placebo injection of just salt water. Federal government started this nationwide program to vaccinate all children, and they say in a few years the disease was conquered. Polio was basically wiped out in the United States in just a few years. So, now imagine you're 7. You're told in October the shots you got last spring were fake. So now you know. So now you have to go get the real one. Now this piques your interest in experiment design when you learn your best friend doesn't need any more shots because they get the real one. And eventually you write a statistics book. Think about the ethics. Some children who got the placebo shot still died or were crippled by a disease when the vaccine might have saved them. But we didn't know that in advance. We didn't know if the vaccine would work. We didn't know if the vaccine might actually hurt them. And like we said, the vaccine is a live vaccine. They weaken it, but it's still alive. What if we didn't quite weaken it enough? And instead, we gave all the kids polio, trying to help them, prevent them from getting it. So ethics is an interesting problem. It's an interesting concern. To me, it's one of the most interesting things about experimentation. What is ethical and what isn't? Okay. Now, the other thing is the experiment actually had a second design where some schools where all the children whose parents approved got vaccinated. And then other kids were just used as controls. Kids who didn't get any kind of vaccine. They didn't even ask for permission. They had a group of kids who weren't going to get the shot. So one design, if your kid volunteered, they got the shot. And they just compare them to kids who didn't get the shot. Now, the interesting thing is, the result of that design was not as convincing. It looks like the parents with higher levels of education were more likely to give permission. But these parents were also more likely to raise their kids in more hygienic conditions. And that actually put their kids at more risk of polio because their immune system hadn't been built up to it by small exposures. So the fun thing is, these kids were more likely to be, these parents, more likely to be highly educated. They were more likely to volunteer, but their kids were actually more susceptible to polio in the first place. So that experimental design was not as convincing as one that used randomization, random assignment. Like we said, children who've been less hygienic, they might have had a mild form of polio very early in life. They had a natural immunity when they got older. Treatment and controls weren't identical at the start of the experiment. It was a confounding result. Big moral of the story, there's no substitute for double-blinded, placebo-controlled, randomized clinical trials. You want to use the 3 or 4 rules of experimentation every time. Now, homework for this section, we have the online portion, and we've got some questions out the textbook. Questions out the textbook are questions Now, I reduced the number of questions out of the textbook, even though they reduce the number of questions out of the textbook. Instead, what we're going to do is from chapter 13, question 1, 3, 14, 24, 27, 32, and 38. All right, got a little audio problem there. Sorry about that. But again, textbook questions, the online questions also. I look forward to seeing you in class.